In this highlight video, we will learn to predict the important intermolecular forces that are taking place with different functional groups and different molecules. We can break molecular forces into 4 different types. We'll start out with van der Waals forces or van der Waals interactions. These are very weak forces, and they are really the most common and the most general types of attractive forces. The next type are the dipole-dipole interactions. These are slightly stronger, and they are important in molecules that have a net dipole. So they need to have polar bonds in order to have dipole-dipole interactions. The next step up along the way is hydrogen bonding. This is really a special type of dipole-dipole interaction. These are quite strong, and they need to have hydrogen atoms that are bonded to more electronegative atoms. The final and strongest type of intermolecular interaction are the ion-ion interactions. These are very strong, and these are present in ionic compounds or salts like sodium chloride, lithium fluoride. They're not so common in organic chemistry, but we can see them in molecules like for the conjugate base of a carboxylic acid. So like this would be paired with a cation. Okay, so these are salts, or another type of salt is an ammonium ion with a plus. So this would be ammonium chloride. So these would be more organic types of salts that have ion-ion interactions. But mostly we will talk about these upper 3 types of interactions. As the polarity of bonds or of molecules increases, so does the strength of the intermolecular forces. So in general, what we see is that plus charges are attracted to minus. So the stronger those charges are, the stronger the interactions. Let's look first at van der Waals interactions. Like I said, these are weak. They are apparent in all molecules, but they're really the only dominant type of intermolecular force in non-polar molecules where other attractive forces are absent. Van der Waals attractions result from temporary dipole interaction. So let's take a molecule like methane, CH4. Carbon-hydrogen bonds are very nonpolar, and so there would be very little attraction between methane molecules. But what happens is if these two molecules get pushed together, the electron cloud in one gets pushed away a little bit relative to the other. We build up a slight amount of delta plus on one side, slight amount of delta minus on the other side, and those partial charges attract each other. So this is only a transient or a temporary attraction, and it's very weak. So the strength of these van der Waals interactions. The first one is the surface area of the molecule. So the greater the surface, the more van der Waals interactions can take place, and the stronger those interactions are. So let's look at 2 different molecules. So this is pentane, so it's a 5-carbon hydrocarbon, and what we see is that because there's a lot of surface area here, there's quite a lot of van der Waals interactions compared to this molecule over here. It's an isomer. It has the same molecular formula, but this one is much more like a ball, and so there's very little surface area contact, and so they're much weaker van der Waals interactions. So these are stronger over here because there's more surface area. Another thing that influences the van der Waals interactions is what we call the polarizability of different atoms. And the polarizability is how easily the electrons can be pushed around to create these temporary dipoles. If the electron clouds are very large, then we say that those clouds are more polarizable, and so that leads to stronger van der Waals forces. So for example, if we have an iodide, so iodomethane, we call it like this, versus a chlorine, so chloromethane, this iodide here is much larger, and so it's much more polarizable, and so this would have stronger van der Waals. Van der Waals interactions. The next strongest were the permanent dipole-dipole interactions. So these are molecules that have polarized bonds. So in this molecule, it has this carbon-oxygen bond. Oxygen is more electronegative than carbon, so there would be a delta minus on the oxygen and a delta plus on the carbon. And so the delta minus of the oxygen here orients to the delta plus on the carbon here, and so there's an attractive force between those two partial charges. And so as you see, these acetone molecules will essentially line up. Delta minus goes to delta plus, goes to delta minus, goes to delta plus. The final type of intermolecular concentrate on are the hydrogen bond interactions. And so like I said before, hydrogen bond interactions are really just a special dipole-dipole type of interaction because we're looking at permanent dipoles, but this type of interaction is only present in certain situations with certain functional groups. So what's necessary is a hydrogen atom that's attached to either an oxygen, a nitrogen, or fluorine, and that hydrogen will be attracted to a more electronegative atom like an oxygen or a nitrogen or a fluorine. So hydrogen bonding interactions are very important in water. Okay, and what we see in water is that we have these polar oxygen-hydrogen bonds. So we have a delta minus on the oxygen and a delta plus on each of the hydrogens. So the delta minus in one molecule gets attracted to the delta plus in another water molecule. And then we have delta minus, delta plus. This delta minus here likewise would be attracted to a delta plus over here. Right? This delta plus over here could be attracted to a delta minus, and a network of hydrogen bonds is created. And so this is really a quite strong situation. These types of interactions are also very important in biological molecules, especially in molecules like DNA and in proteins. So one thing to keep in mind is that all of these intermolecular forces are just attractions. None of them are complete bonds. We call these hydrogen bonds, but they're just electrostatic interactions between a partial minus charge and a partial plus charge. So try on these two problems here to identify what are the important attractive forces for these various types of molecules. In the next video, we'll see how we can apply these intermolecular forces to the physical properties we observe for different organic molecules.